The electrode manufacturing process usually consists of 5 individual process steps, including the slurry mixing, the coating of the slurry onto the current collector foil, the drying of the coated material, the compaction, and finally, the slitting process. Each of these process steps has a large influence on the electrode and cell performance, which can lead to unwanted fluctuations in the electrode quality if not controlled properly, but can also offer the possibility to fit the electrode parameters as needed by changing process parameters. The electrode manufacturing is usually starting with the dry mixing of all powder components. Either in the same device, the wet mixing is done later, or in another mixer specialized in the dry mixing of the components. After the powder components are mixed properly, the pure solvent or a solvent binder solution is added. Following this, the wet mixing process is conducted until we reach a homogeneous slurry. The precise mixing time and mixing intensity, as well as boundary conditions like temperature, pressure in the device, or solid content, have a strong influence on the slurry properties and the quality. The variety of usable mixing devices ranges from small-scale stirrers to planetary mixers and extruders. After this comes the coating process step. The coating of the electrode slurry onto the metal current collector can be done by a self-metered doctor blade or comma bar process, or via pre-metered slot die. The self-metered coating offers the advantages of an easier and less expensive coating process. It is also more flexible and easier to clean. The pre-metered coating with a slot die, on the other hand, can create a much more precise and much more stable coating, but the effort needed to change the slurry is much higher. This is why self-metered coating is often used in research, while slot dies are the standard process for large-scale industrial production. After the coating is done, the electrode slurry has to be dried in order to evaporate the solvent and gain the porous dry electrode structure. The current standard for this is convective drying. However, there are new drying technologies in development, like drying via infrared or inductive drying. During the convective drying, the wet electrode is moved through an oven with a precisely set temperature and air profile. The drying profile has a large influence on the formation of the porous electrode structure, as well as the distribution of the individual components in the electrode. Intense drying can lead to a significant quality decrease of the electrode because of binder migration, but decreases the necessary drying time, which is favourable for industrial production. The following calendaring step fulfills different roles. On the one side, the compression of the coating leads to a higher density due to a decrease in the porosity. Lower porosity means a higher energy density of the cell, as well as a smaller amount of electrolyte necessary, which increases the gravimetric energy. On the other side, the compaction of the electrode leads to a homogenization of the coating and a better electrical connection in the porous structure. This is especially favourable for a lithium-ion battery cathodes, where the active material itself has a low electrical conductivity. The amount of porosity needed for an optimal electrode performance depends on many different factors like targeted C rate or area loading of the electrode. The last step of electrode production is the electrode slitting. The slitting of the continuous electrode band into the right format can be done either by mechanical cutting or by laser. While the laser has much less abrasion and therefore can be used much longer before it needs to be replaced, the mechanical cutting machines are much cheaper to purchase. The cutting quality of both depends on different parameters. For example, the laser can damage the coating at the cutting edges by introducing heat if the pulse time and intensity are not fitting. And the mechanical cutting can lead to the breakage of parts of the electrode at the edges, especially if the adhesion of the coating is not optimal.